All right, so this is malware analysis. I hope if I get to the top, if my thing would move, it won't move, all right? There's no way to get to the top. This happens a lot with computers. Keyboards just don't work right. Anyway, all right, it is Need Tuesday. All right, so we're way down here. All right. And so this is the next to last class. This is the last lecture. We'll do covert malware launching. Then comes the last class. So I won't have any lecture. I'll just be helping people. And then comes the final exam. This semester is pretty much over. So let me get the last lecture, which is chapter 12 here. And there it is. All right, that's nice. Ah, yeah, this garbage. Yes, yes, come on. All right. All right, so we're talking about some techniques which we've talked about before in earlier chapters in less detail. The blaster worm, that was an attack on Windows from the Linux community. I think it was actually from Red Hat, I'm not sure, but there was an argument about who wrote it at the time, was a famous worm that would affect your Windows XP machine, and it would pop up a box saying, your machine is going to shut down in 3 minutes, 250, 240, and you'd have 3 minutes to stop this process, and then it would boot up and say it's going to go down in 2 minutes and a half, and then 2 and 1.5, faster and faster until your machine was unusable. And what you had to do was go in Task Manager and kill the MS Blast process before your machine shut down. That was how it worked. So a simple malware just ran as a separate process, and you could find it and shut it down. And of course, that's too easy to stop, so they try to hide better than that. And so that's what covert launching techniques are. All right, so launchers, the point of these is to run a process and make it hard for the defender to find it and stop it, concealing that malicious behavior. So they usually have one executable, and then they have another executable hidden inside that one in another section, in a resource section typically. So it's just where you'd have some kind of other things there like icons or images and not considered executable, and then it's going to load that and run it. Therefore, it'll be typically encrypted or compressed to make it harder for the scanners and antivirus and everything to find it. And so you'll find things like find resource, load resource, get the size of the resource, and then other routines to decrypt or decompress it. All right. And you'll also typically find privilege escalation you normally want to run as high privileges. All right, so process injection is the most popular technique, DLL injection and direct injection. This is where you add the code to a process that's already running. This is therefore very sneaky. If you look in Task Manager, there will not even be a new process, and you inherit the privileges of the running process, which is nice. So that way you might bypass things like firewalls, for example. If you want to have network connections, you can infect a process that's already approved to reach the network, like Internet Explorer. So you'll find virtual alloc-x allocates space in another process's memory once you get a handle to that process, and you can write process memory. So you can add a section to another process and add code to it while it's running. So DLL injection is the most common technique. We've done this in the projects. This is the easiest way to do it, is just get your process to load another library, and when it loads, it will automatically run the code in DLL main, and so if you use a tool like Metasploit, it will make malware where the malicious activity is right there in DLL main to make this easy, and we've done that in the projects. Although we didn't inject it into a remote process, we just used DLL load order hijacking to trick it into loading from the wrong directory, which is a simpler way to do it. So if you want internet access, and you can't get, normally a Windows firewall will not let just every process connect to the internet. It will block it until you approve it for each process. So you inject malicious code into a process that already has internet access like this. So you've got the launcher malware, and the launcher malware cannot get to the internet, but what it can do is inject code into iExplorer, and iExplorer can get to the internet. So that's how you do it. All right, and so you'll see it's going to create a remote thread, and it's going to use 3 processes. Here's the victim process. It's going to get a handle of the victim process, which it got here. It opens the process. This is going to be the process ID of your process you're trying to attack, like Internet Explorer. Then it's going to do virtual alloc-x, allocate some space in there, size of the library. Then it's going to write into there the DLL. and then it's going to load the library. So that's going to do it. That's going to get the load that DIL library loaded into another process, and then it will run DIL main. So you can see that in the debugger. Up here you're going to see open process, then virtual alloc x, then kernel32.dil, that's the module. I imagine this is probably a fake thing, a fake name. I don't imagine it's the real kernel32. But anyway, you see that it looks very much the same in the debugger. All right, so once you find DIL injection activity, then you can look for strings containing the DIL malicious process, or just put a breakpoint in a debugger. That's one way to watch this happen. And I don't have a hands-on project for this one, but it would be nice. All right, then of course there's direct injection, where you do not use a library, you just inject direct code in. And this is of course more hard to detect, more hard to create, as we talked about before, where you have to write custom code. So you have to write code, you have to figure out how to run the code without trashing the host process. And it took me a while. In the last flare-on I did number 5. I never finished it, but I managed to do this. I managed to inject code that would change the date, so it always thought it was the right date, by adding another section and jumping into the extra section. It can be done. It's just a little bit tricky. You have to write your code carefully. All right, and then there's process replacement, which this is very cute. You trash the running object. You overwrite all of its memory space with malicious code. So you make it stop working and do something different. And you can do this because of the time-sharing nature of Windows operating system. You remember the processor, you might have multiple processors, but anyway, your processor can only do one thing at a time. Or if it's 4, it can do 4 things at a time. But the point is, most of the processes are always suspended, waiting for their turn to get some processor cycles. They spend most of their time waiting to get some cycles, and while they're waiting, you could be changing them. So that's what you do. So you typically replace something like servicehost.exe, which runs with high privileges in the background, hosting a lot of background services, which you usually don't need them all. And so it's in a suspended state. The primary thread is suspended. It's waiting for its turn to get some processor. And so now you can overwrite the code before it runs. So here's process replacement. Create a suspended state, and then create a process. And then unmap, this will release all the memory, unmap the existing memory map, allocate some new memory, write into it, and then set context, and then resume the thread, so it'll start running again. So you can take the running process, rip it all out, replace it with different code, and start it again, and it will continue to run with the privileges and the name it used to have. This is pretty awesome. I was quite inspired by this. We had a time when we were trying to get a teacher who wanted to teach an IoT things class, and the administrators could not get it approved. So I said, we're just going to take another class with a different name and replace it with his class, this process replacement. They didn't ultimately do that, but that's the same thing here, where it's a way to trick the administration into thinking they're teaching one class, but they're actually teaching another. And that's what this thing does to your operating system. Anyway, so thread context restores the environment, and then resume thread runs the malicious code. So that's what you do. You pause it, or change the guts, start it up again, and it carries on, which is pretty cool. And then there's hooks. And this is where it gets silly. I mentioned before, there are so many ways to add code to a Windows process. It will make you sick, and that's why there is so much malware. So those are ways to trick a process into doing the wrong thing. And here's more stuff built into Windows deliberately. Hooks intercept messages. Your operating system has messages that are events that tell applications to do things, like tell them to resume moving again. They've been suspended waiting for something, and there's a message telling it to go again. So you can intercept them, and this is because you might have custom hardware. You might have like a Bluetooth keyboard or something that needs a special driver, so you have to hook all the keyboard events and have them do something different, go to a different driver. So for that versatility, Microsoft has added this feature, and that's great for malware authors too. So whenever a particular message is intercepted, I can create a hook which will run certain code every time that message comes in, like using a DIL. And so you have user who's doing something like pressing keyboard events, moving the mouse, that creates events. It goes to the operating system, and it sends messages to threads which tell them to do things in response to those quotients. But you can use hooks to add another DIL here, which will be loaded before it goes here, and that could be malicious. And that is not breaking Windows, that's using Windows as it was written. It was written to have this ability so you could have some special hardware issue that had to handle things in a different way. So there's local hooks that observe messages intended for a process in the same process, and then the remote hooks go to a different process on the same computer. Not a fairly significant difference, but anyway. Then there's high-level remote hooks that require that the procedure is an exported function, and low-level remote hooks that require the procedure to be contained in that process. So this one can go to a library. This one has to have the procedure in the same process. And again, in practice, it doesn't really matter. These are just minor details of how you write the thing. And so for keyloggers, our place you would do it, you would connect these events, these WH keyboard, WH keyboard LL. Those are the things that are the hooks that catch keystrokes. And so you'd set Windows hook, and you have parameters here, the type of hook, the handle to the DIL or module, the thread ID to connect it to, and so on. And you can also tell it to connect to all threads on the machine. So that's the game. And then it must call next hook X, because there could be a whole series of hooks. So this is like the structured exception handler we talked about before, where you have an exception, and it goes to the exception handler, which will check to handle certain exceptions, and if it doesn't work, it'll go to the next one, and the next one, and the next one, and then go to the operating system one. So it's the same thing with hooks. You might have a whole bunch of hooks. You have an unusual keyboard, an unusual monitor, and some unusual other hardware, and each one of them is hooking things. And your antivirus is hooking things to like examine that file before you open it, and so on. I don't really know if antiviruses use these kind of hooks, but I think they did at least at one time. Anyway, that's what it's there for. So you can load into all threads, which is what you'd have to do if you want to catch all the keystrokes, but that will probably slow down your machine. Now there's extra code, extra libraries running in every process, and you might get caught by an intrusion protection system, but that is what keyloggers do. Other malware doing something less global than keylogging might just target a specific message. Like, for example, if you just want to have a bot, which will just offer remote control of the machine to an attacker and wait for some kind of signal to activate it, then you could just target a Windows message that is not really used much. Like this one is computer-based training, some kind of message to be used if your computer is being used in some limited way. Almost nobody ever is. So you could wait for this message, and then you could send that message to activate your malware. So this next one here is going to load a hook called a malicious DIL called hook.dil, and a procedure address, and it's going to receive this computer-based training message sent to a Notepad thread, which will force hook.dil to be loaded by Notepad. So you see here it is getting the name of the library, and then going to load the library. Here it gets the malware procedure, and here it gets Notepad's thread ID. Then it pushes this event to the Notepad ID and calls set Windows hook XA. So this will send an event to Notepad that's captured by the hook that loads this DIL and runs it in the context of Notepad, which is not something you would probably do with real malware. It's something people often target Notepad for demonstrations and stuff because it's easy and harmless, but of course Notepad is not always running, and Notepad doesn't have any interesting privileges, so it's not a very high-value target. That's why it used to be a while when at CCDC, the defense competition, they said, just check, and if Notepad is running, you're owned. Because people would use Notepad as the carrier for a lot of these exploits. I don't know if they're still doing that. I hope not, because that's kind of silly. But anyway, it was the standard for a while. And then there's another way to do it. We're going to talk about many ways to do the same thing. This thing called detours. Again, it's a way to modify applications. And I think the idea was to take applications written for an earlier operating system and make them run in a later one or something like that. Another way to add extra bits of code. So you add the PE structure to have another section called a detour section. And that has a different import address table, which is what makes me think it's probably intended to handle different versions of the Windows API. So anyway, secdil is the Microsoft tool used to point the PE to the new section. Here's a import name table in the detour section with another bunch of imports. So you can use that instead of the other imports. All right. I don't know if this is exactly how it works, but you know, in Windows, you can right-click a shortcut to an executable and go to compatibility. You can tell it run this as if it was Windows 7, run this as if it was Windows XP. And I'm not sure if that works here, but that's the kind of thing you could do here. You could try to connect to old versions of the APIs or something. Anyway, then there's another couple of, at least one more, APC injection. These are asynchronous procedure calls, and these direct a thread to execute other code before executing its regular path, just like all these have done. So you can do something before running the normal code, and so you can have a queue of these asynchronous procedure calls attached to it, which are things that will be processed when the thread is in an alterable state, which is when it's waiting. So when the thread is not working but waiting, these asynchronous things will happen. So here's, all right, and so you can have them in the kernel, and you can have them in user mode, and they both work with APC injection. So you can inject from user space. You can queue user APC. Your thread must be in an alterable state, which most threads are in most of the time, which means it's waiting. It's not running right now. And the most common call in the Windows API is this wait, where it waits for something. Most of the threads are all the time waiting for some event to tell them it's time to go ahead. And then you can put in a handle to the thread, the function to run, and a parameter for the function. And then it will be in the queue, and it will be run later by that process. So here you open a handle to the thread with open thread, and then you have queue user APC is going to be called with pfn APC. This is going to load a DIL, and then you'll have DW data is the name of the DIL, and SVC host is the thing we're targeting, which I don't see here, but that is commonly what you target. Actually, typically you're going to target something, you target SVC host because it's running at high privileges in the background, and it's a good target to give you high privileges for your malware. And you can do it from kernel space. And this is one of the ways to execute user code from kernel space, which is hard to do. A kernel mode rootkit has difficulty running a user land command. This is one way to do it. You do APC injection to user space into service host. All right. And so here's an example of what that looks like. Insert queue APC. And I think that might be it. I'm rather surprised I don't see a Kahoot link at the end of this. But anyway, it'll do. I should have some Kahoots. Let me bring them up. Matter of fact, I think I have two of them. I think that my slide there was not the version that had the little Kahoot warnings to tell me to go to them. Such is life. There's always something. Yes? There we go. Is Chapter 13 also for today? No, I'm not going to do Chapter 13 this semester. This is the last one. Yeah, there is 12A and 12B. All right. Hello, Mole. All right. I'll wait till the end of the song. All right, so where do launchers put the code? Yep, typically in the resource section. You could do these other things, but that's normally what you do. You put it in the resource section. All right. All right, which one needs a suspended state? Only replace the process while it's in a suspended state. You can't change the code while it's running. That would be pretty horrible. All right, which one requires the most customized code? Yeah, direct injection, of course. DLL injection, you can use a tool like Metasploit to write the code for you because it's generic. But here you'd have to customize your code to match the process you're injecting into. All right, what's the most common covert launching technique? Yep, DLL injection, as we talked about. We've seen how easy it can be. All right, which one uses find resource? That's resource extraction, as you'd imagine, something a launcher would have to do to get the executable it's going to run. So, all right. May I repeat? All right, and we're just going to do the other one. So, that is 12B. Wait for the end of the song in case there's more people coming, but I think this is it. Okay, so which technique manipulates messages from a process to itself? That's called a local hook. I have not used them hands-on. It would be interesting to learn what they are. I'm thinking there's something like Android intents, but I don't know exactly how they work. All right. So which one will hook all processes? Yep, keyloggers will do that to catch key presses going to any window. All right, which technique adds a new section to the file? Yep, those are detours, not APCs, that's not a new section. But detours are a new section, like the relocation section. All right. And what technique lets kernel mode code execute userland code? That's APC injection. Good. All right, and what technique only works when threads are in an alterable state? That's APC injection, yeah. That one's absolutely true. This one here, I think it might be true too, now that I'm thinking about it. But anyway, APC injection is the answer I expected. In retrospect, I should probably take that one out. Anyway. So part of why these things are extra credit, they're never perfectly fair. All right. So there's a winner. All right.